Thanks for the introduction. My name is Stephen. I'm going to be talking about the exact and approximate lifted inference algorithms for factor graphs. So I'm going to start with a motivating example modeling problem. So this is the pigeonhole distribution. So suppose there are 3 pigeons, and they each want to hide in these 2 holes here. And they dislike being placed into the same hole. And there are no quantum pigeons, pigeons that are in multiple holes at the same time. That's not allowed. And we want to know the probability that k pigeons are placed into the same hole. And this would require computing the partition, some kind of counting problem. And my question to you is, does this seem hard? Does this distribution seem like something that existing methods might not be able to handle well? So let's see what happens. So if we want to answer queries about this distribution on pigeons, one thing to do is to convert it into a factor graph, which is something we all have seen before. So we label the pigeons in the holes, and we create a factor graph, which is on the right. And we have the variables, we have the holes in the pigeons. We have the variables which are true if pigeon I is in hole j. So that's what this factor graph on the right tells us here. So each pigeon, there's 2 variables. One is true if it's in hole A, one is true if it's in hole B. So that's the factor graph. The problem, though, is that this factor graph is dense. There's little conditional independence, because as we add more pigeons, they're all going to be constrained to not be in the same hole together. So as we add more and more and more pigeons, there's going to be lots of pairwise constraints between all of these pigeons, which is going to create a lot of density in this factor graph. So it'll have a high tree width, and algorithms like join tree and variable elimination are going to fail on this family of factor graphs, because as we add more and more pigeons, they're all going to be connected to each other. So is hope lost? Is this problem just fundamentally hard? Are we going to be able to solve inference queries for these kinds of factor graphs? And my question is, what kind of structure is there to exploit in this problem? It seems like there should be some. It's a very structured probability distribution, so what does that structure look like? And the answer that I'm going to talk about in this talk is symmetry as a solution to problems like this. So the key observation for this problem is that pigeons and holes are exchangeable. So we can relabel either of them without changing the distribution, because all pigeons are kind of the same and all holes are kind of the same, right? So I have here an assignment of pigeons to holes. Pigeon 1 is in hole A, pigeons 2 and B are in hole B. And intuitively, this should be the same as if we had put pigeon 1 in hole B and pigeons 2 and 3 in hole A, because they don't really care, the holes are the same. Right? So we would like to capture this in our inference algorithms and exploit these kinds of things. Technically, we'll say these 2 states, where a state is an assignment of pigeons to holes, are in the same orbit. So there's some symmetry which connects them together, which is this hole relabeling thing. And these symmetries are going to dramatically reduce the state space of the problem, because there's lots of states which are somehow equivalent, right? They're all in the same orbit. And we want to exploit this. So there's some existing work, which is lifted inference. So lifted inference scales in the degree of symmetry of the probability distribution. It can handle large, dense problems, and it exploits the symmetry property, which is orthogonal to independence. But the problem with existing exact lifted inference algorithms is that you need to give them a relational representation of some sort. They can't handle arbitrary factor graphs. So they can handle these kinds of first-order logic situations where you give some first-order formulas, and then it generates a very dense factor graph. But it exploits the symmetry in the first-order logic setting in order to do inference efficiently. But it can't handle this arbitrary factor graph situation on the right, because there's no higher level relational structure in order to do the symmetry exploitation that is key to these algorithms. So the question is, how can we exploit symmetry in exact factor graph inference? And we're going to talk about that. So our key insight is that these assignments have a natural colored encoding. What I mean, so we do this assignment encoding, and we get this very colorful factor graph over here. And these colors will have an important semantic meaning in this talk. So the black factors are these pairwise constraints between the pigeons. And the red factors are there's no quantum pigeons constraints. You can't have one pigeon in 2 places at the same time. And these symmetries have been exploited in some existing approximate lifted inference algorithms. So this is the class of symmetries that lifted MCMC and other related algorithms exploit. But we're going to have one extra twist, which is going to be that we also encode the variable assignments as colors. So if we have pigeon 1 in hole A, then that variable will be this bright green color. So that means that variable is true. And since pigeon 1 isn't in hole B, that variable node will be white. And we're going to use graph isomorphism tools to find and exploit these symmetries. So now we get to the contribution of this paper. We propose 2 new algorithms. The first is orbit generation. So it's the first example of exact lifted inference for arbitrary factor graphs. And the second algorithm is orbit jump MCMC, which is an approximate lifted inference algorithm that mixes rapidly with some asterisk caveats in the number of orbits. So I'm going to talk about each of these in turn now. And I'm going to spend most of the time talking about orbit generation. Okay, so let's talk about orbit generation. So I would like a simpler example than the pigeonhole example, just to walk us through some of the technical details of what happens here. So consider a complete factor graph. It looks like this. That's just pairwise connections between all the variables. And all of these factors are identical and symmetric. So this means that the probability of a state is entirely determined by the number of true states, because you can always relabel any of the variables because all the factors are the same. So we're going to collect together all of these states that have the same probability here. Fancy animation. And we're going to put them into a table. Okay, so there's orbit 0, 1, 2, 3, and 4, and we'll populate these. So orbit 0 has no true variables, orbit 1 has 1, orbit 2 has 2, orbit 3 has 3, and orbit 4 has 4 true variables. So this is going to be our table. And we're going to use this table to design a lifted inference algorithm. And it's going to have a couple of ingredients. One is we need to be able to efficiently generate one element of each orbit. And 2 is we need to be able to efficiently compute the size of each orbit. If we can do these 2 things, then we can design a lifted inference algorithm. And this I'll show you with an example. So what does this look like? So first, we want to efficiently find one representative of each orbit. So here I've just chosen one entry from each row of that table I showed you 2 slides ago. So we would like to just grab these. We don't want to run through all possible variable assignments and find one example. We want to efficiently find these things. So I've somehow given you these. So each of these has a probability distribution associated with it. It's unnormalized. So we have 5, 13, 21, 2, and 3, arbitrary numbers. These are the probabilities for each of these states. Now we need to compute the size of the orbit. So the orbit size is 1, because there's exactly one way to have 0 true assignments. 4, because there's 4 ways to have 1 true assignment. And then 6, because there's 6 ways to have 2 true assignments. These are binomial coefficients. In general, they might not be, but for this problem, they are. And we can compute the total probability in each orbit efficiently. If you give me the size and you give me the probability, I just multiply them together, right? So 5 times 1 is the total unnormalized probability of being in state 0. 13 times 4 is the total probability of being in state 1, etc. And these things together give us the partition function. We can sum over all the unnormalized probabilities, just taking the totals in the far left column. And from this, we can get this partition function without having to enumerate all possible states. And in particular, we can do it on the order of the number of orbits, if we can do these 2 things efficiently. So this is going to be what we want to scale in, this number of orbits here. Okay. So now the question is, how do we do these 2 things? Now that we know why, how do we do it? So I'm going to tell you how we do the first one, efficiently generate one element of each orbit. So it's going to be a classic breadth-first search. This is something we've probably seen before. So we start with an all-false assignment here, and we augment it. We assign one variable to be true. So this is good. If we just kept this one, we found 2 representatives. These are 2 guys from different orbits, right? But the problem is there's 3 others, right? There are 3 possible other augmentations to this first state. We can color all the other variables true or false, right? But we realize these are isomorphic to the first. We take a graph isomorphism tool, we run it on these factor graphs, and it tells us these guys are isomorphic to each other. So we can prune them. We just take the output of the graph isomorphism tool, it tells us, yes, these are isomorphic. We trim them away. Never look at them again. We only augment the one that didn't get trimmed. So this one on the far right. So this guy gets augmented to these 4. And then we can see these are all also isomorphic to the first, again, using the graph isomorphism tool. And we can continue this process. And this requires linear in the number of orbits times the number of variables. It calls to a graph isomorphism tool, right? Because at any point, we only have 4, if there are 4 orbits, there are only ever 4 unpruned states. Each of those can only have, at most, the number of variables possible augmentations. Okay, So we've called a graph isomorphism tool many times. I hope we're on board that these graph isomorphism tool calls are an interesting reduction. So we would like to exploit these in our inference algorithms. So I'm going to put a green check mark next to that, saying, we have an avenue for doing this. So now how do we compute the size of each orbit? This is kind of spooky. It sounds sharply hard. Counting things, we generally need to be wary of these kinds of problems. But I'm going to show you that it's not. And we're going to use graph isomorphism tools to count things, which is going to be an interesting application of graph isomorphism tools in this problem. So I'm going to give you a pipeline. I'm going to break it down and explain each of the elements of this pipeline in detail. So we want to avoid enumerating the whole orbit, like trying all possible permutations of variables. That's bad, because these orbits can be very large, right? They're these binomial coefficients. They grow very quickly. So we start with this assignment-encoded colored factor graph. And we run a graph isomorphism tool on it, and we get something called a stabilizer group, which I'll tell you about more. We do something called compute the group order, which is efficient, and then we get this orbit size out of that using the orbit stabilizer theorem. So I'm going to break down each of these little steps and tell you why they work. And I'm going to start with the stabilizer group. So the stabilizer group. So question, which isomorphisms preserve or stabilize this coloring so they leave it the same? So we have this one true variable on the top left and these three false variables. So the answer is any permutation of B, C, and D leave this assignment unchanged. So if we permute the variables B, C, and D, it's as if we didn't change the assignments. So this is called the stabilizer group. And graph isomorphism tools can compute this set of permutations for us, and moreover, they can represent it in a compact way. They can give us a small set of generators which tell us this permutation group. So now we have this kind of updated pipeline. We have this assignment-encoded colored factor graph. We run a graph isomorphism tool. We get this stabilizer group, which is actually a small set of generators. It's usually quite small. And then we can do this thing called a group order. Why does this help us? Let's go there. So this is going to use some group theory. So the orbit stabilizer theorem relates the order or size of the stabilizer to the size of the orbit. So what's the orbit size of this? Well, this has four possible. The orbit size of this is 4. And we compute this in this kind of sideways way. We count the number of ways of permuting A, B, C, and D, the uncolored assignment with only one color for variables. And there's 4 factorial possible ways of permuting A, B, C, and D. And we divide that by the number of ways of computing B, C, and D. That's 3 factorial. And we get 4. I hope this is convincing. This is all the technical detail I'm going to give you about why the orbit stabilizer theorem works here. But we do get the right number here, which I think is fortunate. So computing the order of a group, which is like this number of permutations here, given these group generators that I told you about on the previous slide, is a standard problem in computational group theory, and it's efficient to compute in the size of the graph. So I can give you this stabilizer group, this small set of generators. I can run it through a tool called GAP, which is a computational group theory tool. And then it can tell me the order of the group efficiently without enumerating all the possible elements of the group. And in fact, this is an extremely efficient procedure. You can use this order computation algorithm to count the number of configurations of, for example, a Rubik's Cube. And it can count that this Rubik's Cube with 4 possible faces, with 4 individual cubes on each face, has 4 times 10 to the 84 states, which is a tremendous number of states. And it can do this in milliseconds. It's extremely fast. So it can really exploit a lot of symmetry in the problem to count quickly. So here's some proof of concept experiments. We compared against existing exact inference tool called ACE, which doesn't know about symmetries. And on the left, this graph, the number of variables graph counts the number of variables in a pairwise constrained factor graph, the one we've been talking about. And we can see that ACE pretty quickly runs out of time and blows up at around 22 variables. And our orbit generation algorithm will continue to scale pretty nicely as the number of variables increases. And similarly for the pigeonhole problem as we increase the number of pigeons. This is just showing that if you know about symmetry, you can compute this partition function much faster than if you don't. Okay. Now I'm going to talk about orbit jump MCMC very quickly. So it's our approximate lifted inference algorithm with mixing time guarantees. So the problem is that Gibbs sampling can get stuck. So if we have these pigeons and all 3 pigeons in one hole, they don't like that very much. But if we propose a local move, we're often going to get a quantum pigeon, which is a pigeon that's in two holes at the same time, and that you're not going to be able to move to that state, and that's bad. So some existing lifted inference algorithms, like lifted MCMC, exploit the symmetry to jump between orbits. Unfortunately, that doesn't help us much here, because if we're in this all three pigeons in one hole state, and you do a lifted MCMC step, you jump around in the symmetry group, you end up with all three pigeons in the other hole, which doesn't help you move around very much, and you're still stuck. So orbit jump MCMC proposes jumps between orbits. So we do an orbit jump proposal, and we get a very non-local move. So you can skip over a bunch of low probability regions, and it explores the orbit structure of the problem. You're jumping between orbits. You're not just uniformly sampling a new configuration. So you're exploiting the symmetry in order to jump in a relatively low dimensional space, just the number of orbits. So we show how to do this using something called the Burnside process. And we show that it requires multiple graph isomorphism and group order computations. You have to compute the number of configurations in an orbit, which I showed you earlier requires some graph isomorphism and group theory calls. So this is going to be more expensive per step than lifted MCMC, which is nice. It's very fast to do transitions in lifted MCMC. But we're going to have some mixing time guarantees because the effective state space of our orbit jump MCMC algorithm is on the order of the number of orbits. And we actually get a theoretical upper bound on the number of, on the mixing time of this orbit jump MCMC for our pigeon. And we can show that on our pigeonhole problem, this upper bound in the blue dotted line guarantees that we don't get stuck in these low probability states, and lifted MCMC can get stuck. So in conclusion, some distributions have little independence, but inference is still tractable. Symmetry complements independence in these cases. This work develops symmetry as a source of tractability. We give the first exact lifted inference algorithm for factor graphs, and we give an orbit jump MCMC algorithm. And I want to leave with a grand challenge, which is integrating independence and symmetry into a single algorithm for factor graphs. This whole time I've just been talking about number of orbits, but we don't talk about independence in this work, and I think that that's a very nice next step. And with that, I'll conclude and take any questions. Thank you very much for your time and attention.